For the first time in history, a spacecraft has ventured into the Sun's atmosphere. This daring feat by the Parker Solar Probe will be forever remembered in the annals of space exploration. No metal can endure such intense heat, and no rock on Earth can withstand it. This raises the question, why doesn't the Parker Solar Probe melt in this extreme heat? It operates flawlessly even in temperatures of millions of degrees. Welcome back to the World Explorer's Corner videos. In the early 1900s, scientists made a curious discovery while studying the Sun. They measured the Sun's heat by analyzing the wavelength and color of the light emitted by the Sun using spectrographs. You can observe that there is a direct connection between the color of light and its wavelength with respect to temperature. The result that puzzled scientists and remains a mystery to this day was this: the surface temperature of the Sun is about 5,500 degrees Celsius, whereas its outermost atmospheric layer, the corona, has an astonishingly higher temperature of more than 500,000 degrees Celsius. That's at least 100 times hotter than the Sun's surface. It's as if we feel more heat when we move away from a fire. This unique phenomenon has puzzled scientists for the past century. Normally, this layer is hidden by the Sun's intense brightness, and it is only visible during a solar eclipse or with the help of a chronograph sunshade. In 1958, after NASA's establishment, numerous space missions commenced. One after another, satellites and spacecraft were sent into space. However, to comprehend this unique solar phenomenon, it was imperative to create a probe capable of entering the Sun's corona layer to investigate what was transpiring there. This probe needed to study the Sun's emissions even in the scorching heat of 500,000 degrees Celsius. However, this task was far from easy. The Sun's extreme heat is challenging to fathom. For instance, iron has a melting point of 1,500 degrees Celsius, and tungsten, the toughest metal in the world, melts at 3,422 degrees Celsius. The Sun's heat would swiftly liquefy these metals. Now, consider the corona layer, where temperatures reach millions of degrees. How can anything endure such conditions? Designing and developing the Parker Solar Probe presented a considerable challenge, but even more daunting was getting it close to the Sun, which is tightly bound to our solar system's planets. Firstly, if you wish to return a satellite from Earth's orbit to Earth, its speed must be reduced to enable Earth's gravity to pull it back. Similarly, if you intend to send a spacecraft to another planet, its speed must be increased to escape Earth's orbit. Let's suppose you want to send a spacecraft to Mars. It is first placed in Earth's orbit using rockets. Subsequently, it is launched out of Earth's orbit at the precise moment, angle, and speed required. Removing a spacecraft from Earth's orbit demands a significant amount of energy. Rockets are used to reach Earth's orbit, but there are no rockets once the spacecraft is there. Hence, the small rocket within the spacecraft is employed to gradually increase its speed and take it out of orbit. Mars is relatively close to the Sun, so the angle at which the spacecraft is launched is not excessively steep. However, the distance between the Sun and Earth is 150 million kilometers, requiring a substantial angle and energy to take it out of Earth's orbit and place it into the Sun's orbit. The requisite energy and power had never been developed until that point. Therefore, NASA experts decided to send the Parker probe to Venus before aiming it at the Sun. Venus, the second planet in our solar system, could help increase the probe's speed with its gravitational pull. Nevertheless, there was a challenge. Venus is a smaller planet, which means it has less gravity. To reach the necessary speed to approach the Sun, the Parker probe had to circle Venus 24 times to get closest to the Sun. On August 12, 2018, the Parker Solar Probe was launched from Cape Canaveral Air Force Station. NASA planned an 8-year mission for this endeavor. To reach the Sun's closest point, the probe will rely on Venus's assistance 24 times. Each orbit takes 37 hours, during which the Sun is steadied. Over the course of 8 years, this probe will amass 900 hours of research on the Sun. On April 28, 2021, NASA confirmed that the Parker probe had successfully entered the Sun's corona layer during its 8th orbit. Indeed, the corona layer is 100 times hotter than the Sun. But what causes this extraordinary temperature difference? Research is ongoing. Now, let's address our primary question: why doesn't the Parker Solar Probe melt in such extreme temperatures? The side of the Parker probe facing the Sun is equipped with a heat shield made of carbon. This isn't an ordinary shape. It was specifically designed by the Ultramat company to absorb the Sun's heat. This shape is 97% empty, which enhances the heat shield's effectiveness. A layer of carbon-carbon composite, produced by blending graphite and resin, is applied to both sides of the heat shield and superheated to make it the purest form of carbon. As we all know, carbon has excellent heat conductivity. Furthermore, the side of the heat shield facing the Sun is coated with white ceramic paint to maximize sunlight reflection and minimize heat absorption. The rest of the Parker Solar Probe is designed to remain in the shade of this shield. Nevertheless, even with these precautions, the Parker probe can only withstand temperatures of up to 200 degrees Celsius, while the corona's temperature reaches 500,000 degrees Celsius. It is now clear how the Parker Solar Probe endures such extreme heat. According to the laws of thermodynamics, a medium is required to transfer heat. In the same way, during the summer, particles and vapors in the air carry heat within themselves, causing us to feel hot even at night. When there are fewer particles, heat does not transfer as easily. For instance, if we were to place our hand in boiling water, it would burn immediately. However, if we were to place our hand in a 300-degree oven and quickly remove it, we might not even feel the heat. This is possible because water molecules make contact with our skin, while nothing within the oven makes contact with us. Experts explained that the Parker Solar Probe's heat shield reaches temperatures of up to 1,200 degrees Celsius. In contrast, the side not exposed to the Sun's rays experiences temperatures below freezing because there are no particles present to transfer heat. This is why the Parker Solar Probe does not melt, despite its proximity to the Sun. We hope you enjoyed this video. Please like and share it. Thank you for your wonderful comments. See you in the next video.